consider the two-body problem in 2 dimensions and the calculation of orbits. An object is located in 2D space and on a 2D graph by 2 coordinates, the x or horizontal coordinate and the y or vertical coordinate. So a position function must specify an object's x coordinate and y coordinate and can be written as shown with 2 components, px of t and py of t. Velocity in 2D is a vector and has horizontal and vertical components as shown on the graph, and hence the velocity function has 2 components, vx of t and vy of t. Similarly, the acceleration function has 2 components, ax of t and ay of t. Now we have a very brief trig refresher. Given a right triangle with an included angle theta, the sine of theta is defined as the ratio of the lengths of the opposite side of the triangle and the hypotenuse. The cosine is defined as the ratio between the lengths of the adjacent side and the hypotenuse. Note that the sine and cosine are well defined, and it doesn't matter if the right triangle used to define them is large or small, as the ratio of the sides doesn't change. Also, MATLAB has built-in sine and cosine functions that take their arguments in radians. Now we want to resolve the force of gravity acting on a satellite located with coordinates x, y, and the Earth located at the center of the graph into its x and y components. The distance between the satellite and the Earth can be computed with the formula for r shown, and the magnitude of the force of gravity can be computed with Newton's formula, which is also shown. The force of gravity is directed along a line from the satellite to the Earth, and that line makes an angle with a horizontal axis, which we've labeled theta. Note that the sine of theta equals y over r, and the sine of theta also equals f of gy over f of g, so that f of gy, i.e. the y component of the magnitude of gravity, equals f of g times y divided by r. Similarly, the cosine of theta equals x over r, and it also equals the magnitude of the x component of gravity over the total magnitude, so that the x component of the magnitude of gravity equals the total magnitude of gravity times x divided by r. And we've resolved gravity into its x and y components. With gravity resolved into its x and y components, we can compute the total acceleration a and resolve it into its x and y components. Then, with Newton's law of motion applying to each coordinate, we have the model for the trajectory, and we can write the update equations. The model will have 4 state variables: position and velocity for the x-coordinate and position and velocity for the y-coordinate. And the computational equations are shown. The x position at time ti plus 1 equals the x position at time ti plus the x velocity at time ti times dt. The x velocity at time ti plus 1 equals the x velocity at time ti plus the x acceleration at time ti times dt. And the x acceleration at time ti is the total acceleration times the x position at time ti divided by r, also evaluated at time ti. And similarly for the y component of position and the y component of velocity. So we're about ready to go. All that is required to generate an orbit is the correct initial state, i.e. position and velocity, for the orbit to be created. The image shows a depiction of the space station orbit, and that's what we'll generate first. The space station has an average altitude above the surface of the Earth of 402 kilometers and an average velocity of 7,706 meters per second. It makes one complete trip around the Earth every 96 minutes. We'll use Earth-centered inertial coordinates. That is, the coordinates don't rotate with the Earth for the program. So we can picture the center of the Earth as being at the center of the coordinate system. Let's generate some initial values for this simulation. We'll start the satellite on the horizontal axis. So its initial x coordinate will be the radius of the Earth plus 402,000 meters, and its y coordinate will be 0. We'll give it initial velocity in the y direction, that is straight up looking at the graph. So the x component of velocity is 0, and the y component is 7,706 meters per second. The graphs show the results of running the simulation. The outer circle is the generated satellite orbit, and the inner circle is an outline of the Earth, which we added to the graph at the end of the program. The code for adding the outline is shown here. The first command is a hold command, which tells MATLAB we're going to add a graph to the existing graph. The for loop generates the x and y coordinates for 100 points on a circle, and then the plot command plots the circle that we just generated. Then we give the hold off command to restore MATLAB to its normal state, where each plot command generates a new graph. So your assignment is to write, debug, and run the program that generates the space station orbit. That might seem like a formidable task, but there's some help available. The help comes by way of a program outline, which I will include for this program and all the programs assigned in the course. It is important that you write, debug, and run the programs yourself. However, if you're new to programming, this might seem like a daunting challenge. So I want to suggest an approach for learning to program. First, try to write the program yourself without reference to the outline, beyond getting the values for the necessary constants, which I'll include in the outline. Every program in the course will have the same basic structure. It starts with an initialization section where constants and parameters are initialized. Then there's the for loop, which projects the state variables over the subintervals. All that you need for the for loop is a formula for the velocity of each state variable, which is the model. The third and final section is the plot statement and optionally additions to the graph, like the outline of the Earth in this example. So make an attempt to write the program unaided. Fix the syntax errors. Run the program and try to debug it. However, don't beat your head against the wall. After you feel you've exhausted all your options and don't know what to do next, and the program still doesn't work, consult the outline. Then try to fix the program using the outline as a guide. Then fix any new syntax errors which you just introduced, and again try to debug the program to get some good results. However, again, don't beat your head against the wall, and when your frustration threshold is reached, consult the reference program, which can be found by following the class notes link in the description. That is, compare your program to the reference and correct your mistakes one by one, and keep at it until your program is running. After you do this a few times, you'll get more adept at making fewer mistakes and getting the program to run on your own. This, I believe, is the best way to learn programming, by doing it.